Hey everyone, welcome back. Today we're taking a deep dive into something pretty amazing, graph neural networks.
GNNs, yeah.
Or GNNs for short. And we're going to be focusing specifically on how they're being used in wireless communication and networking.
Right.
Now, we know you guys out there, our listeners, you're already familiar with machine learning, but GNNs, that might be a bit of a new frontier for some of you.
Yeah.
So think of this deep dive as your crash course, your express lane into the world of GNNs and how they're really changing the game in wireless communication.
Absolutely.
So to keep things organized, we're going to break this down into three main areas. We'll start off by really understanding what GNNs are, what makes them tick, and why they're such a natural fit for the challenges we face in wireless networks.
Okay.
Then we'll move on to looking at how GNNs are being used to tackle real-world problems at the physical layer.
Right.
So we're talking about things like optimal power allocation, beamforming, making sure those signals are strong and clear where they need to be. And then finally, we'll zoom out a little bit and go up to the networking layer.
Okay.
We'll see how GNNs are being used for routing, scheduling, even creating these super fast network simulators that can really speed up research and development. Now, I don't know about you, but I am already geeking out just thinking about all this.
It's really exciting stuff.
It is. So let's bring in our expert to guide us through this fascinating world of graphs.
All right, happy to be here. So let's kick things off by talking about a fundamental shift that's happening in machine learning these days.
Okay.
So traditionally, we've been very focused on individual data points.
Right.
You know, treating them as kind of isolated entities.
Right.
But now the real power is in understanding the relationships between those data points.
Ah, okay.
And what better way to represent relationships than with a graph, right?
A graph, I could see that.
So think about your wireless network.
Okay.
You've got your devices, your base stations, your users. All of these can be nodes in our graph.
Okay.
And those communication links between them, those are the edges in our graph.
Ah, okay.
And we can even weight those edges based on things like signal strength, interference levels, you name it.
Oh, I see, I see. So it becomes like a visual representation of the entire network and how everything is connected.
Exactly. It captures the whole structure and those crucial interactions.
That's cool.
Now, there were some earlier attempts to learn from graphs, things like Deep Walk and Node2Vec.
Okay.
But they kind of hit a wall. They weren't very scalable. You couldn't easily add new nodes to the network. And they completely ignored those valuable node features that we have in wireless networks.
Right, right. Each device has its own unique characteristics.
Exactly. And those characteristics can be really important for making good divisions.
Okay, so what was the breakthrough? What came after that?
That's where GNNs step in, graph neural networks.
Ah, code GNNs.
They're designed to overcome those limitations.
Okay.
So first off, they share parameters across the entire graph, which makes them incredibly scalable.
Ah, so it doesn't matter how big the network gets.
Exactly.
Yeah.
And then new nodes.
Yeah.
No problem. They could adapt on the fly.
Okay.
And most importantly, they can actually use those node features to gain deeper insights.
Ah, so they're not just looking at the connections, they're looking at what's at each node.
Precisely. They're taking everything into account.
Wow, okay. So I'm intrigued now, but how do they actually work? I mean, what's the magic under the hood?
All right, so one of the key concepts here is what's called a message passing neural network,
Message passed.
or MPNN
Yeah.
for short. Picture each node in the graph having a little chat with its neighbors,
Okay.
sending messages back and forth, sharing information.
Or like gossiping about the network.
Kind of.
Yeah.
And each layer of the GNN, it aggregates information from those immediate neighbors.
Okay.
So as we stack more layers, we're essentially expanding each node's sphere of influence.
So it's like a ripple effect spreading through the network.
Exactly. It starts locally and then expands outward.
Oh, I see. Mathematically, each layer can be described by equations that update a node's information based on what it receives from its buddies.
That makes sense.
Now, this MPNN framework has actually given birth to a whole family of different GNN architectures.
Oh, well.
You've probably heard of graph convolutional networks, or GCNs.
GCNs, yeah.
They're kind of the rock star in this world,
Yeah.
and they're very powerful and widely used.
Right. All right. So we've got these powerful GNNs that can understand relationships, can handle complex networks. But let's bring it back down to earth a little bit. Why are they so well suited for the specific challenges that we face in wireless communication?
Right, good question. So it really comes down to a few key properties of GNNs that align perfectly with the nature of wireless networks.
Okay.
So first off, scalability.
Scalability, okay.
Real-world networks are constantly growing and changing.
Right.
GNNs are built to handle that. They can be trained and tested on networks of all shapes and sizes.
So they can grow with the network.
Exactly, no matter how big it gets.
That's important.
And then second, distributed implementation.
Okay.
In a decentralized wireless network, you don't want all the processing happening in one central location.
Right.
Creates bottlenecks. It's not very efficient.
Yeah.
But GNNs, they lend themselves naturally to distributed computation because that message passing we talked about, it can happen locally between neighbors.
Ah, so each node is kind of making its own decisions based on what's happening around it.
Exactly. No need for a central brain calling all the shots.
I like that. I like that.
And, in wireless networks, optimal decisions, they often depend on local information.
Right.
Interference levels, channel conditions, nearby devices, all that stuff. GNNs capture that local awareness beautifully.
It's like they have their finger on the pulse of what's actually happening on the ground.
Exactly. But here's something even cooler. GNNs are inherently permutation equivariant or invariant.
Permutation equivariant. Okay, now you're just using big words to try and impress me.
Haha, fair enough. But it's a really important concept. What it means is that if you shuffle the nodes around in a network, the underlying communication principles, they stay the same.
Okay.
GNNs understand this inherent symmetry.
It's like rearranging the furniture in a room.
Exactly.
The room is still the same, just the layout has changed.
You got it. And this symmetry awareness, it gives GNNs a huge advantage in wireless networks. It's different from how, say, convolutional neural networks or CNNs work in image recognition.
Yeah, CNNs, those are for images.
Right. CNNs exploit translation invariance. They understand that an object in an image is the same whether it's in the center or off to the side.
Okay.
But GNNs, they're all about the connections, regardless of where things are physically located.
So CNNs are about location in space, while GNNs are about relationships, connections.
Precisely. And this leads to a really exciting approach where we can blend those classic wireless algorithms, the ones that we've been using for years, with these data-driven GNN modules.
So we're not throwing out the old stuff, we're just giving it a boost.
Exactly. We get the best of both worlds. We get the insights of those established models, combined with the flexibility and learning power of GNNs.
Okay, I like that. All right, so we've laid the groundwork. We kind of understand the basics of GNNs now.
Yeah.
Now I'm really curious to see how this all plays out in practice. Are you ready to jump into some real-world examples?
Absolutely. Let's start with the physical layer. That's where GNNs are already making a big impact.
All right, lead the way. Okay, so we're diving down to the physical layer. What's happening down there? What are GNNs doing at this level?
So down at the physical layer, it's all about making sure those wireless signals are getting where they need to go.
Right.
And one of the biggest challenges we always face is interference.
Yeah.
Right? Too much interference and your network's going to slow to a crawl.
It's like trying to have a conversation in a crowded room. Everyone's talking over each other. Nobody can understand anything.
Exactly. So one of the main weapons we have to fight interference is power allocation.
Power allocation.
And that basically means dynamically adjusting the transmit power of different devices to try to squeeze out as much network capacity as possible.
It's like finding the right volume for everyone in that crowded room so that everyone can be heard without shouting each other down.
Perfect analogy. But, it gets really tricky when you have tons of devices all trying to talk at the same time.
Yeah, real-world networks are messy.
They are. Channel conditions are changing constantly. You need solutions that can adapt quickly. That's where GNNs can really shine.
Okay. So how are they being used for this power allocation problem?
Well, one powerful approach we're seeing is this idea of domain-inspired learning.
Domain-inspired learning, okay.
And that basically means we're combining the best of both worlds. We're taking those classic wireless algorithms.
Right, the tried and true stuff.
Exactly, and we're giving them a GNN boost. We're using GNN modules to enhance them and make them even better.
Okay, so we're not throwing out those classic algorithms. We're just making them smarter.
Exactly. So let me give you a good example.
Okay.
Let's take the classic WMMSE algorithm. It's a well-known algorithm for power allocation.
Okay.
It works, but it can be a bit slow. Sometimes it gets stuck in suboptimal solutions, and it doesn't always take advantage of all the extra information we have about the network.
Right. It's like it's working with one hand tied behind its back.
Yeah, kind of. So that's where the GNNs come in.
Okay.
Imagine you have a network with multiple transmitter-receiver pair.
Mm-hmm.
And you want to find the optimal power level for each transmitter, right?
Okay.
So traditionally, you would use the CSI, the channel state information,
The CSI,
which
right?
basically tells you how well the signals are propagating between devices.
Okay, like a map of signal strength.
Right. But GNNs, they can go a step further.
Oh, okay.
They can incorporate not only the CSI, which we represent as a weighted adjacency matrix of our network graph, but also node-specific information.
Node specific, like what?
Well, things like queue length
Okay.
or user priority. So each node has its own, unique characteristics.
Right.
And we can feed all that into the GNN.
So it's getting a much richer picture of the network, not just those raw signal strengths.
Precisely. It's understanding the whole context.
Okay.
And that allows GNNs to learn a direct mapping from all this combined information to the best power settings. It's almost like we're teaching the GNN to be a power allocation expert.
Ah, okay. It's learning from all this data and figuring out the optimal way to adjust the power.
Exactly. It's figuring out those complex interactions that influence power allocation. And there are some interesting GNN architectures out there that are doing this really well, like RGNN and IDCNet.
RGNN and IGCNet.
Okay. So RGNN, it uses a standard kind of layered approach.
Mm-hmm.
Each layer gathers information from a wider neighborhood in the network.
Okay.
And IGCNet, that one focuses on actually computing the pairwise interference between neighbors.
So two very different approaches.
Right. Right.
Both using GNS.
Yeah, and both achieving good results.
Okay.
Now, there's another really cool approach we should talk about. It's called algorithm unrolling.
Algorithm unrolling. Okay, that sounds interesting.
It is. So what we're doing here is we're actually taking the steps of an existing algorithm, like that WMSE algorithm we talked about.
Mm-hmm.
We're taking those steps and turning them into layers of a neural network.
Okay.
Then we use GNNs to refine those steps.
Ah, okay. So we're using the algorithm as a starting point, but then letting the GNN kind of learn and improve upon it.
Exactly. And one specific method that does this really well is called UWMMSE.
UWMMSE.
Unrolled WMMSE.
Okay.
And it's achieving some really impressive results. It's getting near optimal sum rates. It's running faster than the original WMMSE algorithm, and it can adapt to changes in the network.
Wow, that's amazing. So we've tackled power allocation. But, things get even more complex when we start talking about MIMO systems.
You're right.
Multiple antennas.
Yeah.
Beamforming.
Right. So with MIMO, we're not just controlling the power. We're also controlling the direction of those signals.
Right. It's like having a spotlight. You can adjust how bright it is, but also where it's pointing.
That's a great way to think about it. So we're trying to focus the signal towards the intended receiver and minimize interference with other devices.
Right. More precision, but also more complexity.
Definitely. But the good news is we can extend that UWMMSE method we talked about to handle MIMO as well.
Okay, so the same basic idea, but adapted for a more complex scenario.
Right. And in this case, the GNNs are actually learning to optimize both the power allocation and those beamforming vectors.
The beamforming vectors, right. Those determine the direction of the signals.
Exactly.
So UWMMSE, it's a bit of a multi-tool then.
It is.
Handles both those simple single antenna cases and the more complex MIMO cases, all with the help of GNNs.
Yep. And the results are really impressive. UWMMSE is outperforming other state-of-the-art methods in terms of both achieving high data rates and doing it quickly.
That's awesome.
Yeah.
So we've covered power allocation in different forms, but I know there's another area where GNNs are making a splash, and that's federated learning.
Right.
So how do they fit into that world?
So in federated learning, you have multiple devices that are all working together to train a machine learning model, but they don't share their raw data.
Right. They just share their model updates.
Exactly. And power allocation, it's crucial here because those devices need to upload their local model updates to a central server.
Okay.
And we want to do that as efficiently as possible. We have to consider delay, energy consumption.
Right. We don't want devices draining their batteries too quickly.
Exactly.
Yeah.
And we also have to consider that different devices might have very different data.
Right.
Some might have lots of data to upload. Others might have very little. So it's a pretty tricky problem.
It sounds like it. So how are GNNs helping with this?
Well, researchers have developed a really interesting GNN called PDG.
PDG.
It stands for Primal Dual Graph Convolutional Power Network.
Wow, that's a mouthful.
It is. But basically, it's a GNN that's specifically designed to handle the challenges of power allocation in federated learning.
Okay.
And it works in 2 stages.
Okay.
First, it learns a power allocation policy based on the network structure and the goals of the federated learning task.
Right.
And then during each iteration of the learning process, it applies that policy to determine the optimal power level for each device.
It's like it's giving each device a personalized power plan.
Exactly, to
Okay.
make sure those model updates are sent efficiently and contribute effectively to that global model.
That's really clever.
Yeah, and the results are promising. PDG is leading to lower transmission error rates, and it's significantly improving the overall performance of federated learning.
That's awesome. So we've seen how GNNs are optimizing the physical layer. We've looked at power allocation in different forms, beamforming, even how they're being used in federated learning. I'm ready to move up the stack now.
Yep.
What can GNNs do with the networking layer? Okay, so we've explored the physical layer. We've seen how GNNs are making things more efficient down there. But now I want to zoom out a bit and look at the networking layer.
Okay, yeah.
It's like we're moving from, fine-tuning the engine to managing traffic flow on a massive highway.
Right.
What kind of challenges are we dealing with at this level?
So at the networking layer, it's all about making sure that data gets where it needs to go. Smoothly, efficiently, reliably.
Okay.
We're talking about things like routing, finding the best paths for data packets to travel through the network, and link scheduling, making sure those paths are being used effectively.
Ah, okay. So it's like air traffic control, but for data packets.
Exactly, making sure everything flows smoothly, no collisions, no delays.
But I imagine these tasks, they can get pretty complicated.
Oh, absolutely. We're often dealing with these incredibly complex combinatorial optimization problems.
Combinatorial optimization. Okay, now you're just using big words to scare me.
No. But it basically means you have a ton of different options.
Okay.
And you're trying to find the absolute best one.
Okay.
It's like trying to find the shortest route through a city with thousands of streets, and the traffic patterns are changing every minute.
Yeah, that sounds like a nightmare.
It can be, especially in a wireless network where nodes can move around. Channel conditions are constantly fluctuating.
Right. It's a very dynamic environment.
It is. And to make things even more challenging, we often need solutions that can be implemented in a distributed manner.
Distributed is okay. So each node has to kind of make its own decisions.
Right. Based on its local information. You don't want everything relying on a central controller.
That makes sense. So where do GNNs fit into all of this?
Well, as we've seen, GNNs excel at learning from graph structures. But they can't always handle the hard constraints that come with these networking problems.
Hard constraints, what do you mean?
Well, for example, in link scheduling, you can't have 2 devices transmitting on the same channel at the same time if they're within range of each other.
Right. That would cause interference.
Exactly. It's a fundamental rule. You can't break it.
Okay, so how do we combine the flexibility of GNNs with those hard and fast rules?
That's where a really clever framework called GDPG Twin comes in.
GDPG Twin.
Yeah, it stands for Graph-Based Deterministic Policy Gradient Twin.
All right, I'm going to try and remember that. But tell me, what's the basic idea?
So think of it as a team effort.
Okay.
You've got the actor. That's a GNN that proposes actions, like which links to schedule, which routes to choose.
Okay.
Then you have the critic, another GNN that evaluates those actions. It provides feedback on how well they're working.
Okay.
And then to make sure the actor doesn't suggest anything crazy, anything that breaks the rules, we have a traditional algorithm acting as a safety net.
Ah, okay. So it's like a system of checks and balances.
Exactly. The actor proposes, the critic evaluates, and the algorithm makes sure everything stays within the lines.
I like that. So let's see how this GDPG Twin thing actually works in practice.
All right, so one type of problem where it's really effective is what we call independent repetitive combinatorial optimization problems.
Wow, that's a mouthful.
It is. We just call them independent archipelags for short.
Independent archipelags, okay.
Think of it as solving a series of related puzzles.
Okay.
Each puzzle represents a network optimization problem, like, for example, scheduling links to maximize throughput.
Okay.
And the independent part means that we can solve each puzzle individually without worrying too much about how our solution will affect future puzzles.
So each puzzle is self-contained.
Right.
It has its own optimal solution.
Exactly. And in this setting, the GNNs in GDPG Twin, they learn to recognize patterns in the network structure and use that knowledge to make better decisions.
Okay.
So one concrete example is using GDPG Twin for the maximum weighted independence set problem.
Maximum weighted independence set.
Yeah, it's a classic problem in link scheduling. Basically, you're trying to find the largest set of links that can be activated simultaneously without causing interference.
Okay, so finding that balance between maximizing throughput and avoiding those conflicts.
Exactly. And GDPG Twin has shown really significant performance gains over traditional methods for this problem.
Wow. Okay, that's impressive. But what about those cases where decisions do have consequences down the line?
Right. Good point. So, in many scenarios, what you do now can affect what happens in the future.
It's like a game of chess. You have to think several moves ahead.
Exactly. So in these cases, the GNNs in GDPG Twin, they have to step up their game.
Okay.
They not only need to encode the current network state, they also need to learn to predict those future rewards based on the actions taken.
So it's a more strategic approach.
It is. And one example where this is really important is delay-oriented link scheduling,
Okay.
where the goal is to minimize the time it takes for data to travel through the network. You're not just trying to avoid interference, you're trying to get those packets to their destination as quickly as possible.
So latency becomes a key factor.
It does. And what's amazing is that GDPG Twin can achieve performance comparable to much more complex reinforcement learning methods.
Really?
Yeah.
But in a more efficient way.
Exactly. It's much more computationally efficient.
That's great. So we've seen how GDPG Twin can be used for those independent RSIPs. And those scenarios where decisions have long-term consequences. Are there any other applications for this framework?
Oh, absolutely. It's incredibly versatile. You can apply it to things like back pressure routing in wireless ad hoc networks.
Back pressure routing.
Yeah, the goal there is to avoid congestion by making smart routing decisions.
Okay.
Or you can use it for congestion-aware distributed task offloading,
Okay.
where you're trying to decide which devices should share the workload to minimize overall congestion.
So it's like a master traffic controller for the whole network.
That's a good way to think about it.
All right. So I'm really impressed with this GDPG Twin thing.
Yeah, it's a powerful tool.
But there's one more area I want to touch on before we wrap up, and that's those super fast network simulators that you mentioned earlier.
Right.
The digital twins.
Yes.
So traditional network simulators, they can be really slow, right?
They can.
It takes a lot of time to run those simulations.
It does. They're very computationally intensive.
Yeah. So how are GNNs changing that?
Well, we can actually use GNNs to create these digital twins of the simulators.
Okay.
So essentially, we train a GNN to predict the key performance indicators of a network. Things like delay, jitter, throughput,
Okay.
packet drops, all those important metrics. And it can do that much faster than running a full-blown simulation.
So it's like a shortcut.
Yeah, it is. It's a way to get those results without having to wait for the simulation to crunch all the numbers.
And that could be a huge time saver.
It can. And it opens up a lot of exciting possibilities.
Like what?
Well, we can evaluate network designs much faster. Okay. We can try out different configurations. We can even use these GNN-based simulators to train other machine learning models for network optimization.
Wow. So it's like we're using machine learning to turbocharge our network simulations and then using those turbocharged simulations to design even better networks. It's a really cool feedback loop.
It is. It's a really exciting area of research.
Yeah.
And one specific GNN architecture that's doing this really well is called PlanNet,
PlanNet.
which stands for Path, Link, and Node Network.
Okay.
And it's achieving incredible prediction accuracy while being orders of magnitude faster than traditional simulators. We're talking about 1,000x speedups or more.
Wow, that's amazing. It's like having a crystal ball that shows you how your network will perform.
It really is. And, this is just the beginning. GNNs are a relatively young field, but they have immense potential in wireless communications and networking.
Well, I have to say, I'm really excited about the future of GNNs in this space.
Me too. It's a fascinating field.
We've seen how they can optimize the physical layer, manage traffic at the networking layer, even speed up the way we design and evaluate networks. It's been an amazing journey.
It has.
So for our listeners out there, the key takeaway is that GNNs are incredibly powerful tools for learning from the complex relationships in wireless networks.
Yeah.
They can be used on their own or in combination with those traditional methods that we've been relying on for so long. And they're being applied to a wide range of problems, from power allocation and beamforming at the physical layer, all the way up to routing, scheduling, and even simulating entire networks. GNNs are really transforming the landscape of wireless communication.
They are.
And as the field continues to evolve, the possibilities are truly limitless.
Absolutely.
So that's it for our deep dive into GNNs. Thanks for joining us. We hope you found this episode insightful, and we hope you're as excited about the future of this technology as we are. Until next time, keep exploring, keep learning, and keep pushing the boundaries of what's possible in wireless communication.